Hi everyone. Today we're going to start with chapter 7.3, Estimating a Proportion. So our objectives for today are going to be to check the random and large counts condition for constructing a confidence interval for a population proportion. We're also going to determine the critical value for calculating a C% confidence interval for a population proportion using Table A or technology. All right. So this is what we often want to do when we make a confidence interval. We're trying to answer this question about our population. Let's say we want to know what proportion of U.S. adults are unemployed right now. It's something that we would want to figure out, and a confidence interval could help us get a nice estimate of values. We also might want to know what proportion of high school students have an iPhone. Again, these are numbers about our population that we might want to know about, and although we may not be able to get the exact answer, we can get a nice, accurate confidence interval about. All right, so before we construct an interval, which we've been kind of leading up to today, there are some conditions that we have to satisfy. So I want you guys to write down the two conditions that you see there in that table. And that is the random condition, which says the data come from a random sample from the population of interest. And also the large counts condition, which would look familiar from a few chapter ago. N times p hat should be greater than or equal to 10. And also for this one, n times 1 minus p hat also should be greater than or equal to 10. In the previous chapter, we were able to do this problem using just n times p. But now, the focus and the emphasis on this chapter is that we don't know p. It's something we want to find out. So that's why we use our p hat, or what we call our point estimate or our statistic. All right, and this involves gives us a sampling distribution that's approximately normal. This just ensures that we're able to use this normal curve like we use it a lot in chapter 6. All right. So on this example, we have a random sample of students who completed the Census at School survey. And there was 227 students in the sample, and 84 reported that they had allergies. We want to estimate the true proportion of students with allergies in that population of students. Now, we're just going to check to see if our conditions are met. All right, so here we have a p hat of 84 over 227. If you grab your calculator, 84 over 227 is 0.37 is our p hat. All right, so in the next slide, I'm going to show you how we're going to use that to figure out if our conditions are satisfied. All right, so number one, was it random? Yes, it was. There was 227 students that were randomly selected. As long as the problem says random somewhere, we're going to assume it was like an SRS or done in some other truly randomized manner. Large counts, as you guys wrote down on the previous slide, n times p hat has to be greater than or equal to 10. In this case, 227 times 0.37 gives you roughly 84. We're just going to round up to the whole number, and that gives you 10. And likewise here, 0.63, which comes from 1 minus 0.37. That's 0.63. So remember, n times 1 minus p hat, and that gives us roughly 143, which is greater than or equal to 10. So our conditions are satisfied. Okay, please pause the video and try this out. And in about a minute, we will go over the solution and see if you guys are doing okay. Okay, so here, according to a recent study by the Annenberg Foundation, only 36% of the adults in the U.S. could name all three branches of government. And this was based on a random sample, survey of a random sample of 1,416 adults. All right, so here notice they gave you p hat right away. Nothing to divide or nothing to calculate. And that p hat is 0.36. Always write it as a decimal. Don't write it as a percentage. All right, so that is 0.36. So using that, you should have been able to calculate for the large counts condition, 510. Again, we round up to a whole number if we need to. And then here, 1,416 times 0.64, that would be 0.64. That gives you about 906, and both are comfortably over 10. And again, also was the random condition, and the problem did say that the sample was collected randomly. So we are good to go on this condition. All right, so now we're going to move on to this idea of a critical value. So you have learned earlier in this chapter, in chapter 7, that a confidence interval is made up of two parts. All right, you've got this makes a confidence interval. It's made up of a point estimate and something called a margin of error. Now, what you're going to see shortly, maybe not necessarily today, is to get the point estimate, we're just going to use p hat. And it's as simple as that. But the margin of error is a little bit more difficult. The margin of error involves something called a critical value and also the standard deviation. Okay, now if you look down here, we've talked about something called the 68, 95, 99.7 rule. And in summary, we would use a critical value of 2 for 95% of all samples, because in the 68, 95, 99.7 rule, 95% of all your observations are within 2 standard deviations of the mean. And that would typically be a critical value for a 95% confidence level. But we're going to go a little bit more in depth. So this is just a little bit of background, and if you're not too sure about this, don't worry. But we are going to use this standard deviation formula that you learned in chapter 6, radical p times 1 minus p over n. Okay, it's going to look very similar to that. It's not actually exactly like that, but it's going to look very similar to what you see there. And we're going to spend more time talking about that tomorrow. But right now, the important part is, what's the critical value? How do we figure that out? So that's what we're going to look at next. All right, so please write this down, and I'll read it for you, but pause the video if you need to write it down. It is very important. So the critical value is a multiplier that makes the interval wide enough to have the stated capture rate. And we are going to, for this section, represent it with what we call Z star. That's going to represent our critical value, Z star. Okay, so as long as the large counts condition is met, we can use a normal distribution. And the reason why there's a Z there, is because, it ties into the idea of Z-scores. All right. All right, so here it says use table A or technology to find the critical Z star value for a 90% confidence interval. Here we're going to assume the large counts condition is met. All right, so on your calculator, I'm going to focus on a technology, just using technology as opposed to table A. And I'll show you how to use Statplet as well, because when I give you your quiz, you can use any resource on the internet, so I'll show you both ways. So if you have a TI, you're going to tap second vars, which gets you to the distributions, and you're going to go use something that we've used before called inverse normal, INVNORM. And since we want a 90% confidence interval, you're going to type in an area of 0.90. But the way a confidence interval works is that this is your center area. Okay, 0.90, mu 0, standard deviation 1, take the center area, and you will see a negative value and a positive value. Your Z star is the positive value, and just go ahead and round it to the nearest hundredths place. So the Z star critical value for a 90% confidence interval is 1.65. This would be our answer. Okay, now let's say you don't have a TI. I totally understand. You are going to go to Stapplet, stapplet.com. There's 2 P's. Okay, go to normal distributions and probability and look for normal distributions and click on that. And you're going to change the operation to calculate a value corresponding to an area. And make sure your mean is 0, your SD is 1, and you want 90% in the central area of 0.90. And you'll see the critical value right down here. 0.90 gives you a critical value. Again, we're going to round to 1.65. All right, and here what I did is you can see the shaded region and how it cuts it off right in between 1 and 2, but more specifically, it cuts it off at 1.65. And this is negative 1.65. But your critical value, your Z star, is the positive value that you get. Now, one last thing before we move on to our last problem here is in these 2 tails, because you have 90% in the center, you've got 10% left to split in between the 2 tails. Now, the reason why I'm telling you this is because on a TI-83, when you use inverse norm, you typically have to give the left tail area. And you would have to type in inverse norm of 0.05, and it would give you a critical value of negative 1.65. So if you have a TI-83 and that's an issue, send me a Schoology message or Google Classroom message, and I can help you with that. But just keep that in mind because you can calculate critical values in that manner also. Okay, last problem. Please pause the video and try these 2 out. I do want you to sketch it out and then write the Z star critical value for both. Okay, welcome back. So here I have screenshots of Stapplet and how you would do this. So the Z star for a 95% confidence interval is 1.96. Okay, so there's an area in the center of 0.95. Z star is 1.96, and you can see right here how close the shading is to the number 2. And remember, the 68, 95, 99.7 rule should actually have a standard deviation difference of 1.96. We usually round it up to 2 just to make it easier when you're first learning it. But technically, at 95% confidence, your values are 95% of your values are within 1.96 standard deviations of the mean. It's technically not 2. Technically lied to you guys. It's actually 1.96 to be more specific. Okay. Now for the 99% confidence interval, that's an area of 99%. Your Z star is 2.58. And again, I'm rounding up 2.576, rounding up to 2.58. All right, if you guys have any questions, please don't hesitate to send me an email, send me a message on Schoology or Google Classroom. If there's a problem on the homework that you don't understand, send me a message early, and I'll write it out and I'll post it on Google Classroom for not only you and everyone else in our class to benefit from. All right, have a great day, everyone. Take care.